Most people think the next leap in artificial intelligence will come from a bigger GPU. NVIDIA is betting it won't. While everyone was arguing about who has the fastest AI chip, NVIDIA quietly started connecting AI processors with quantum computers. Not replacing one with the other, connecting them. That single distinction matters more than most headlines suggest. Because AI has reached an awkward point. Every new model demands exponentially more computing power, more electricity, more cooling, and more money. Training frontier models is becoming so expensive that only a handful of companies can even attempt it. Scaling forever isn't a strategy, it's a bill. So NVIDIA has started looking somewhere else. This isn't science fiction. The company has been building what it calls accelerated quantum supercomputing, linking its AI GPUs with quantum processors through a platform designed to let each machine do what it does best. Classical AI handles enormous data processing. Quantum hardware tackles calculations that would overwhelm even the fastest supercomputers. That doesn't mean your laptop is about to become a quantum computer next year. It means something much more important. The rules of computing may be starting to change. And history has a habit of rewarding the companies that write the rules before everyone else realizes a new game has begun. There's another reason this deserves attention. The race isn't only about technology anymore. It's about who controls the computing infrastructure that every future industry depends on. AI, pharmaceuticals, defense, financial modeling, advanced materials, even climate simulations are all competing for computational resources. Whoever builds the platform everyone depends on doesn't just sell hardware, they shape entire industries. Think back to the smartphone revolution. The companies that made phones earned plenty of money, but the companies that built the operating systems became gatekeepers for billions of people. NVIDIA appears to be chasing the same position for the next era of computing. That's a much bigger ambition than selling graphics cards. To understand why, we need to talk about a problem the AI industry rarely advertises. Today's AI systems are astonishing at recognizing patterns, generating language, and analyzing massive data sets. But underneath the impressive demonstrations lies a simple reality. They're still limited by classical mathematics running on classical hardware. Some optimization problems become so complicated that even the world's fastest supercomputers grind through possibilities one after another. Imagine trying every key on a giant keyring until one opens a lock. Classical computers are incredibly fast at trying keys, but they're still checking them sequentially. Quantum processors don't work that way. Without getting lost in physics, they exploit quantum mechanics to evaluate certain kinds of problems in fundamentally different ways. They're not universally faster. In fact, for many tasks, they're worse than ordinary computers. But for specific calculations involving optimization, molecular interactions, or quantum systems themselves, they could eventually outperform classical machines by astonishing margins. That's why pharmaceutical companies, chemical manufacturers, and national laboratories have spent years investing in quantum research, despite its obvious limitations. The potential payoff is simply too large to ignore. Here's the twist, though. Quantum computers aren't replacing AI. They're not replacing GPUs either. They're becoming teammates. It's a surprisingly practical idea. Let AI manage workloads, correct errors, optimize algorithms, and translate complicated quantum operations into something researchers can actually use. Meanwhile, quantum processors attack the narrow class of problems where they have an advantage. It's less like replacing a pilot and more like giving the pilot a completely different instrument panel. Even the timing feels deliberate. Just as competitors race to build larger language models, NVIDIA is investing in what comes after larger models stop being enough. Maybe that's brilliant. Maybe it's too early. But when one of the world's most valuable technology companies starts redesigning the relationship between AI and quantum computing, it's usually worth asking what they can already see that everyone else is still debating. Because once we follow the trail of that question, the strategy becomes much bigger than quantum chips alone. The first company to understand this wasn't NVIDIA. It was Google. Back in 2019, Google announced that its quantum processor Sycamore had achieved what it called quantum supremacy. The experiment itself wasn't commercially useful. In fact, IBM immediately argued that a classical supercomputer could probably perform the same task, just much more slowly. The debate became a headline, but the real lesson had nothing to do with who won the argument. It proved that quantum hardware had moved beyond laboratory theory. That mattered. Since then, IBM has introduced increasingly capable quantum processors. Companies like IonQ and Rigetti have pushed alternative architectures, and governments from Washington to Beijing have poured billions into quantum research. China reportedly invested heavily through the Chinese Academy of Sciences and the University of Science and Technology of China, while the United States responded with funding through the National Quantum Initiative. Everyone saw the finish line. Almost nobody agreed on the road leading there. Because quantum computers have a problem that rarely makes the headlines, they're extraordinarily fragile. A tiny vibration, a slight temperature fluctuation, or even stray electromagnetic interference can introduce errors. Many quantum processors must operate at temperatures colder than outer space, just a fraction of a degree above absolute zero. Building the processor is difficult enough. Keeping it stable is another challenge entirely. That's where NVIDIA saw an opening. Instead of waiting for quantum hardware to become perfect, it asked a different question. What if AI could compensate for quantum's weaknesses? That sounds almost too convenient, but it's becoming one of the industry's most promising ideas. Modern AI systems excel at pattern recognition. Feed them enough operational data, and they begin spotting relationships that humans would likely miss. Quantum systems constantly generate mountains of diagnostic information: noise levels, error rates, calibration changes, hardware drift. AI can monitor all of it in real time. Imagine driving through heavy fog while someone sitting beside you continuously adjusts the headlights, steering sensitivity, and navigation based on conditions you can't even see. The road hasn't changed. Your ability to stay on it has. That's essentially what NVIDIA is trying to build. Its CUDA-Q platform combines the company's GPU ecosystem with quantum programming tools, allowing researchers to simulate quantum algorithms on classical GPUs before running them on actual quantum hardware. That sounds technical, but the practical impact is straightforward. Researchers spend less time waiting, less time debugging, less time guessing why an experiment failed. Those savings matter because quantum computing isn't limited by ideas anymore. It's increasingly limited by engineering efficiency. Here's something else that's easy to overlook. NVIDIA isn't manufacturing quantum processors itself, at least not today. Instead, it's becoming the company connecting everyone else together. Whether a customer uses superconducting qubits, trapped ions, neutral atoms, or photonic systems, NVIDIA wants its software, networking technology, and AI infrastructure sitting in the middle of that workflow. That's a familiar strategy. The company followed a similar path during the AI revolution. It didn't create ChatGPT. It didn't invent large language models. Yet nearly every major AI company, from OpenAI to Anthropic to Meta, depends heavily on NVIDIA hardware. Selling the shovels during a gold rush turned out to be an extraordinary business. Selling the roads between multiple gold mines might be even better. There's also a geopolitical dimension hiding beneath the engineering. Quantum computing has quietly become another strategic technology, alongside semiconductors, artificial intelligence, and advanced manufacturing. Governments increasingly view leadership in these fields as national security priorities, rather than purely commercial opportunities. If quantum systems eventually accelerate drug discovery, logistics, defense simulations, or cryptography, then the infrastructure supporting those systems becomes strategically valuable as well. That's exactly where NVIDIA is positioning itself, not at one endpoint, in the center. And if that strategy succeeds, the biggest winner of the quantum race may not be the company that builds the most powerful quantum chip. It could be the company every quantum chip has to work with before it becomes useful. That possibility changes how we should think about the entire industry. Because the biggest obstacle ahead isn't building a better quantum computer. It's deciding whether quantum computing is even the breakthrough everyone has been promised. There's a question that almost always appears whenever quantum computing comes up. What if this is another technology that's permanently 5 years away? It's a fair criticism. Quantum computing has been surrounded by enormous promises for decades. Every few years, another breakthrough arrives, another record is broken, and another prediction says practical quantum machines are just around the corner. Yet your phone isn't powered by one. Neither is your car. Neither is your bank. That gap between expectation and reality has created plenty of skepticism, and some of it is deserved. Because quantum computers are not universal replacements for classical computers. They're specialists. They excel at a narrow family of problems while performing poorly on many everyday tasks. Nobody is going to browse the internet on a quantum processor, just as nobody uses a Formula One car to buy groceries. This is where the story takes an unexpected turn. The success of NVIDIA's strategy doesn't actually depend on quantum computers becoming mainstream tomorrow. It only requires them to become useful in a few industries. Think about pharmaceutical research. Developing a new medicine often means simulating how molecules interact at the atomic level. Those interactions quickly become so mathematically complex that researchers rely on approximations. Better approximations mean better drugs. Faster simulations mean treatments reach patients sooner. If quantum processors shave months or eventually years off that process, pharmaceutical companies won't care whether the rest of the world is still using classical computers. The economics speak for themselves. The same logic applies to battery chemistry. Finding materials that store more energy, charge faster, and last longer is essentially an optimization problem involving countless molecular combinations. Testing them physically takes years. Simulating them accurately could dramatically shorten that timeline. Suddenly, the race isn't about building a cooler computer. It's about discovering better medicines, stronger materials, and more efficient factories before your competitors do. That's a very different incentive. Here's the reversal that changes how I look at NVIDIA's announcement. I don't think the quantum chip is the most valuable part of this partnership. I think the AI GPU is. That sounds backwards until you consider what today's quantum systems still lack. They need software, they need simulation, they need error correction, they need orchestration across thousands of calculations. Almost every one of those tasks plays directly into NVIDIA's existing strengths. In other words, quantum hardware may be the headline, but AI infrastructure could quietly become the engine making the entire ecosystem practical. It's a bit like the early internet. People remember the websites. Far fewer remember the routers, servers, networking equipment, and operating systems that actually made those websites possible. Infrastructure rarely gets applause. It usually gets paid. There's another layer to this that deserves attention. The competition is no longer happening inside a single country. The United States has companies like NVIDIA, IBM, Google, Microsoft, and numerous quantum startups pushing different technologies. Europe has firms working on photonic and neutral atom systems. China continues investing heavily through state-backed research institutes and companies, viewing quantum technologies as strategically important for both commercial and national security applications. Nobody wants to discover that another country solved a commercially valuable quantum problem first. Not because of prestige, because the first breakthrough could reshape entire industries. Imagine one nation dramatically accelerating fertilizer development, aircraft design, advanced semiconductor materials, or logistics optimization, while everyone else is still relying on conventional computation. The advantage wouldn't stay inside laboratories. It would flow into manufacturing, exports, military capability, healthcare, and eventually everyday economic competitiveness. This is why governments continue funding quantum research despite the uncertainty. Walking away carries its own risk. Personally, I still have doubts about the timeline. We've underestimated the engineering challenges before, and it's entirely possible that practical, fault-tolerant quantum systems take longer than investors expect. But I wouldn't dismiss NVIDIA's move because of that. The company isn't betting on a single breakthrough. It's positioning itself to benefit whether quantum computing arrives in 5 years, 10 years, or even later. That's a much safer strategy than trying to predict the exact moment the technology matures. And once you recognize that, another question starts to matter even more. If NVIDIA is preparing for a future that hasn't fully arrived yet, who else is already quietly rearranging their business around the same assumption? For decades, the technology industry has been obsessed with a single question: who builds the fastest chip? I'm starting to think that's becoming the wrong question. The more interesting one is this: who builds the system that lets every kind of chip work together? That's where NVIDIA's strategy begins to make sense. Its GPUs remain the workhorses for training AI. Its networking business connects thousands of processors into giant clusters. Its software ecosystem keeps developers inside its platform. And if quantum processors become commercially useful, NVIDIA wants them plugged into that same environment, instead of operating as isolated scientific instruments. Notice the pattern. The company isn't trying to win one race. It's trying to own the roads connecting every race. History suggests that's often the more profitable position. Railroads made fortunes without mining gold. Cloud providers became indispensable without creating every application. Operating systems became trillion-dollar businesses without manufacturing every computer. Infrastructure quietly compounds. That's why I don't believe this announcement is really about quantum computing. It's about reducing uncertainty. If quantum computing succeeds, NVIDIA is already there. If progress is slower than expected, NVIDIA still dominates AI infrastructure. If another company invents a superior quantum processor, NVIDIA can still provide the software, networking, and accelerated computing needed to integrate it into real-world systems. Very few technology strategies cover that many possible futures. Of course, there are real risks. Quantum hardware still faces enormous engineering obstacles. Error correction remains one of the industry's biggest challenges. Building large-scale, fault-tolerant quantum computers could require years of breakthroughs that nobody can schedule on a calendar. Competition is becoming more intense as well. IBM continues advancing its quantum roadmap. Google is investing heavily in quantum error correction. Microsoft is pursuing its own long-term approach. Specialized startups are experimenting with trapped ions, photonic systems, neutral atoms, and entirely different architectures. China is unlikely to slow its investment either, given how strategically important quantum technology has become. There may not be a single winner. Different industries could end up using different quantum architectures, just as today's computing world relies on CPUs, GPUs, and specialized AI accelerators simultaneously. That would actually strengthen NVIDIA's position if its software remains the common language connecting them. Here's my opinion. People often assume technological revolutions happen when a magical invention suddenly appears. Most don't. They happen when dozens of technologies become useful together. The internet needed broadband, servers, browsers, and operating systems. Modern AI needed GPUs, massive datasets, cloud computing, and transformer models. Quantum computing may follow the same path. The processor itself is only one piece. AI, software frameworks, networking, advanced cooling, and classical supercomputers may all mature together until one day people say, "It happened so fast." It probably won't feel fast while we're living through it. One doubt still stays with me, though. Will quantum computing deliver enough practical value to justify the enormous investment pouring into it? Or will expectations once again outrun reality? We don't have that answer yet, and anyone claiming certainty is probably selling something. My prediction is a little different. Within the next decade, the biggest breakthroughs won't come from replacing AI with quantum computers. They'll come from AI and quantum systems working together on problems neither could solve efficiently alone. Drug discovery, advanced chip design, energy storage, and materials science are likely to be the first industries where that collaboration becomes commercially meaningful. If that prediction proves correct, this week's headlines won't be remembered because NVIDIA connected two different kinds of processors. They'll be remembered because this was one of the first visible steps toward a new computing architecture, one where no single chip does everything, but each one amplifies the others. And sometimes, that's how the biggest shifts begin, quietly. If you enjoyed this breakdown and want more deep dives into the technologies shaping the balance of global power, subscribe and join me in the next one. The next chapter of computing probably won't arrive with a loud announcement. It'll arrive one connection at a time.